Welcome to Institute of Quality and Reliability. Hi, this is Hemant.
Response Surface Designs Part 2 Central Composite Design with Application Example. Response Surface Designs Part 2 Creating a Response Surface Design and Analyzing for Optimization of Response. We recommend that viewers should watch our Part 1 of this video on Response Surface Designs before watching this video. Link is provided in the description of this video. In the Response Surface Design Part 1 video, we have explained how to add center points to a factorial design and analyze the experiment to assess presence of curvature or nonlinearity. In this Part 2 video, we will explain the structure of response surface designs with focus on central composite designs, illustrate how to create and analyze a response surface design, analyze, interpret a response surface experiment and illustrate how to optimize a response using Minitab software and a virtual catapult. In an RSM, a second order model is fitted instead of a linear model. Second order model for a two-factor RSM is given by y predicted is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 1 2 x1 x2 plus beta 1 1 x1 square plus beta 2 2 x2 square. The last two terms with x1 square and x2 square are the quadratic terms which get added with a response surface model. There are two popular response surface designs used. One, central composite design, the short form is usually CCD. This is the most popular class of designs for RSM. It was introduced by Box and Wilson in 1951. Generally, the CCDs would consist of 2 to the power k full factorial or fractional factorial designs of resolution 5. It can be used in sequence with earlier factorial designs by adding or augmenting appropriate actual points and response information. The second type of design is Box-Behnken design. This is used sometimes when there are certain types of constraints. For fractional factorial designs and resolution of designs, watch our video on this subject. Link is provided in the description of this video. Let us now understand the structure of a central composite design with two factors. The figure shows a full factorial design with two factors A and B. The center point of the design is coordinate 0, 0. And the coded factor levels are +1 and -1, that is at coded distance of 1 unit from the center point. In central composite designs, the factorial or corner points are augmented with actual points. These are also called the star points. The number of star points is twice the number of factors. In this case, there are two factors and therefore there will be 4 actual star points. If the distance of the factorial points or corner points from the design center is plus or minus 1 coded unit, then the actual points are at a distance alpha as shown in the figure. For a two-factor central composite design, the number of corner points will be 4. Number of actual points NA will be equal to 2 times the number of factors K, that is equal to 4. Number of center points will be equal to 5. This is the default number and you may reduce or increase. Total points or runs will be therefore 13. For a three-factor design, the number of corner points equals 8. The number of actual points NA will be 2 times the number of factors K, that is equal to 6. And the number of center points will be equal to 6. This is again the default number. Total points or runs will be equal to therefore 20. These are the actual or star points in a three-factor central composite design. The most commonly used central composite design is the circumscribed design. The number of points in the factorial portion of design equals NF.
In this circumscribed design, recommended default distance alpha of actual points from the center equals nf raised to the power 1/4.
Thus, for a 2 to the power 2 design, number of factors equals k, that is equal to 2. Therefore, nf equals 4, and therefore alpha will be equal to 4 raised to 1/4, and that is equal to 1.414. And for a 2 to the power 3 design, number of factors k equals 3, and therefore nf will be equal to 8. Therefore alpha equals 8 raised to 1/4, and that equals 1.682.
Let us see the three typical options used in case of central composite designs. The first option is circumscribed design. This is also the default option. The coded levels of the factors are plus or minus 1 unit from the center of the design space, while as the actual points are placed at alpha, which equals nf raised to 1/4, where nf is the number of points in the factorial portion of the design.
Second option is face-centered design. The coded levels of the factors in this design
Are placed at plus or minus 1 unit as usual,
and the actual points are also placed at alpha is equal to 1. And the third option is inscribed design, wherein the star points are set at coded levels of plus or minus 1. Remember, these are the star points which are now set at plus or minus 1 coded level, while as the factorial points are set at 1 upon alpha from the center. So the factorial points are actually inside the star points. So it is a scaled down design of the circumscribed design.
one of the desirable properties of response surface designs is rotatability of these designs. The design should provide good predictions throughout the region of interest. One way to define good is consistent and stable variance of the predicted response at points of interest. And a design is said to be rotatable if it has the same variance of the predicted response at equal distances from the center of the design, that is on spheres. Let us now see how to create a central composite response surface design with two factors in Minitab software. We use the stat command DOE response surface, create response surface design. Here we have two choices, central composite and box Benken. We will use the central composite option. The number of continuous factors is 2. If we click on display available designs, for two factors we can see that for an unblocked design we will see 13 runs. So we click OK here. In the designs, we select full with single block. Now in the number of center points, we can choose default, and default will be 5 here. And in the value of alpha, the default will be, you can see that the default alpha is shown as 1.414, which is nf raised to 1/4 as we have seen before. If we choose face centered, alpha will be equal to 1, and we can also choose a custom value. We will keep the default value so that alpha will be 1.414. Number of replicates is only 1. We click OK. The factors will just keep A and B, and we will keep the coded values which are -1 and +1. We click OK here to create the design, and it has given that for two factors with single replicate, base runs are 13, total runs are 13. And we go to the worksheet now. Here we can see we will arrange the design in the standard order so that we can see it little easily. Display design, standard order. So we can see that the -1 and +1 points are all the factorial points or the corner points. And these are the actual points. We show alpha values -1.414 plus 1.414 and then -1.4 plus 1.414 in the factor B. So factor A, these two are the star points or actual points for factor A, and the next two are the star or actual points for factor B. Similarly, if we create a face-centered response surface design with two factors, we can see the following output with alpha equal to 1 in Minitab software. Now let us create a circumscribed central composite design for two factors for a virtual catapult. We will use the same factors and levels as in RSM Part 1 video. These are shown below for reference, but we will add actual points to that design and create a new design. We have shown before how to create a response surface design in Minitab. We use the stat DOE response surface, create response surface design command. We have the central composite design option. We will use two factors. In the display designs, you know that for two factors, for unblocked, it is 13 runs. So in the designs, we choose that design and default value of alpha, which is 1.414 for two factors. We will create a single replicate. So we click OK here. Now we input the factors and levels. So the first factor is firing angle. The low level is 110 and the high level is 130. And the second factor is release angle. Low level is 150 and high level is 166. And we click OK here. In the options, we will randomize the runs. And now let us see what design is created by Minitab. There are two factors. The replicates is 1, base runs are 13 and total runs are 13. Observe that alpha is 1.414. Now let us look at the worksheet. So this is the design which is created. It is listed in run order. So first let us list out the design in standard order by stat, DOE and display design command. We'll select standard order. At the moment we'll keep in uncoded units so that you can see the actual values of the settings. So it has created the 13 runs. Note that when Minitab creates the design, the corner points have code for the point type as 1. These are the corner points. The -1 shows the actual points. So these are the 4 actual points. And 0 shows the 5 center points. You can of course list the design in coded units also, where you will see that alpha value. So stat, DOE, display design. Now we'll select coded unit for a short while, and you can see these 4 actual runs having alpha value of 1.414. So it is -1.414 plus 1.414 for factor A, and then same values for factor B also. We have seen this before. So I will again list the design in uncoded units. And now we will run this and record the values of the distance. As you know, for actual conducting and running the experiment, we must list the design in run order again so that it is randomized. So stat DOE, display design, and run order. Now the first run here is the actual point 105.8 and 158. So we will say 106 and 158, and let us see what result we get on this. So I'll open the Sigma Zone catapult. We set the catapult for the first run. For that we set the firing angle to 106 and release angle to 158. And we see that the distance is 395. We enter value 395 in the first row. Similarly, we will perform all the runs and enter the values. Here is the Minitab worksheet with distance as the response in column C7. Now we are ready to analyze this response surface design, for which we click Stat, DOE, Response Surface, Analyze Response Surface Design, and select Distance as Response. In the terms, we select all, that is full quadratic, and then click OK. In the graphs, we need 4 in 1, so it's already selected. And then in the results, I think we leave it to default. In the storage, we can select fits and residuals, so that we will store the fitted values, that is predicted values, and the residuals, which are difference between observed and predicted values. So we click OK here, and the first thing that we can see is the residual plots, wherein we can see that the residual errors are normally distributed as the points are close to the straight line. The versus fit, residuals versus fit, are reasonably in a parallel band, so that the variation all throughout is quite even. So we can say that this is satisfactory. The histogram may not be representative because of the low sample size, and the versus order is just a random order and doesn't show any significant pattern. So we go to the analysis of the design by going to the session folder, and we look at the response surface regression, and we can see in the ANOVA table, which is here, first we look at the p-values, and we note that p-value for release angle into release angle, that is release angle squared, is 0.892, which means it is not statistically significant. The rest of the rows are statistically significant. The lack of fit is 0.145, which means that the model is satisfactory. If the lack of fit value would have been less than 0.05, which is the alpha risk, we would say that the model is not fitting well on the data. The pure error MS, that is mean square 25.5, indicates that the variance of the replicates of the 5 center points is 25.5. So the standard deviation will be square root of that, which is approximately 5. The model summary shows first value of S as 7.043, but this is a standard deviation of the residuals based on the model. After fitting the model, whatever residuals are there, this is the standard deviation of those residuals. The R square value 99.56 is satisfactory. Adjusted R square is also good. Predicted R square is 97.58. So these are quite satisfactory values. Then we see the coefficients in coded units, and after that we see the regression equation in uncoded units. This is used for contour plots and all predictions and optimization. But as the release angle squared term is not significant, we can omit this. So we go back to the previous command by Control E clicking. In the terms, we select B into B, that is BB, and click on the left arrow to omit that term, and click OK, and just repeat the analysis. And now residuals are still satisfactory, we can see that. And in the session window, we go back and see now the reduced model output, wherein we can see that all p-values are less than alpha risk, so all terms are satisfactory. The lack of fit value, p-value has further increased 0.2, so model is fitting. The pure error is same because there is no change in those center point, 25.5. The residual error has reduced to some extent, 6.59, and R square predicted has also increased to some extent, 98.08. And then the final regression equation in uncoded units is also given. Now we are ready to plot the contour plots and main effect plots and the surface plots. First, let us plot the factorial plots, for which we go to stat DOE response surface and factorial plots. All terms are selected, so no term is omitted. All terms are included in the output. We can see clearly a curvature for firing angle, which means that it is a nonlinear model for firing angle. While as for release angle, we have removed the square term, so it is a straight line response. On the right side, we can see the interaction plots, which shows the curved lines. Now we plot the contour plots. So stat DOE response surface contour plot. Distance is already selected as a response, and there are only two factors. So we click OK and see the contour plot. In the contour plot, if we right click and select the crosshairs, then we can move the crosshairs on the contour plot, and we can see the setting of firing angle and release angle, and also the predicted distance on the left hand top corner. Now the contours, you can see the curvature because of the second order effect or nonlinear effect of the firing angle. And suppose we want to find out what are the solutions for 400, then we can follow this edge, which is for 400, and all these values are giving you predicted response for 400. Now after that, we can also see the surface plot. So we see stat DOE response surface and surface plot. Again, response is selected. There are only two factors, so we just click OK. This is the surface plot, and we can see the non-linearity. On the axis of firing angle, we can see that there is a non-linear response, whereas on the release angle side, it's only a linear response as expected. You can rotate this around different axes like this and bring back to the position by clicking home. So that's about the surface plot. And finally, we can use the response optimizer, stat DOE response surface and response optimizer. And let us say we want to put a target of 300, and we say setup. The lower limit we give as 290, upper limit we give as 310, and in the results you may give a number of solutions to display as 5, so that it will give you a few options for the settings. And we can click OK here to see what the optimizer gives you. So it has given a predicted response of 300 with a D value of 1. D is a desirability value, which 1 means 100%, because we gave a target of 300 and it is predicting 300. So it is 100% achievement of the target. The CUR or the current settings are the recommended settings in the solution, 134.14 and 161.36. These are the suggested solutions. So we can try this solution on the catapult, but before that, let us check in session windows for the other solutions. This is the optimization plot, and these are the 5 solutions. Okay, it has given 3 solutions, not 5. For all these 3 solutions, the fitted value or predicted value is 300. So we can try on the catapult the settings which are recommended. The firing angle is 134 and the release angle is 161, and see what we get. Yeah, it has given 306 value now. So we can check the process capability for this. We had given the tolerance of plus minus 10, which it may be approximately meeting. To summarize, we have explained the structure and options of central composite response surface design and illustrated how to create and analyze the design on Minitab software using a virtual catapult.
Thanks for watching this video. Hope you found it worth watching. Please subscribe to Institute of Quality and Reliability channel if you want to watch more videos on reliability engineering, Six Sigma and statistical quality control. Click the subscribe and bell icon for getting intimations on the future videos.